Okay, so as mentioned, question 1, we have gone through 1A to 1D, and here are the answers. I think the more challenging one is 1D. Many of you did not realize that the question was asking you about self-polymerization. What can polymerize on its own? All right. Finally, I think the rest are quite straightforward. Okay. Now, if you got any of these wrong, the chapters to revise are obvious. It's organic chem. All right. And this is actually already quite a straightforward way of testing organic chem in the O-levels itself. I actually didn't change the O-level questions. So if you got any of these wrong, it's time to sit down with the organic chem notes and revise them. Okay. So that is the answers for 1A to 1F. Okay, I shall now move on to question 2 very quickly. Again, question 2 is rather straightforward. It's just a recall. It also was taken from the O-levels. All right, international O-levels. So firstly, we have given you a few noble gases from group 0. So they ask you to name the noble gas. Noble gas. They are not asking you to name the gas. It's a noble gas. The most abundant noble gas is argon. Some of you wrote nitrogen by mistake. This means that you are not reading the questions closely. They wanted a noble gas. Next. For many years, we have not tested recall. You must have the recall knowledge. Part B tested that. What is one used for neon? Sadly, many of you gave things that were vague or incorrect altogether. Neon is not used for lighting. Lighting is a very vague term. Neon is specifically used for red advertising lights. All right. So even if you got your answer correct, can you please write this answer down? Red advertising lights, so that you know and you must remember. Now, at this juncture, since we are on the topic of noble gases, what are the uses of helium and argon? Now, helium is a very, very light noble gas. Therefore, helium is used to fill balloons. That's one. Helium is also used for weather balloons. Okay? Can also be used for weather balloons. So these are balloons containing instruments to measure and monitor weather. Now, why is helium used for this purpose? Helium is used for this purpose because it has a very low density. Right? Next, argon. Now, argon, you need to know. Argon is used to provide inert atmosphere for reactions. So you can see that the first three noble gases, helium, neon, and argon, they don't have the same functions. They don't have the same uses. You have to memorize it, sadly. All right? Now, next, part C. Many of you lost marks, not because your chemistry answer, answer was wrong. It's just that you did not notice this. All right? You need to state the electronic structure of argon. In your answer, you must have said, argon has an electronic structure of 288. You have to state it. You can't just say it has a fully filled outermost electron shell. You must first state 288, then go on to say, so it has a fully filled outermost electron shell. Now, up to this stage, it's only 1 mark. It's 2 marks though. So what more should you say? You have to address why is it unreactive. How would you do that? When things react, they must either lose, gain, or share. Because the outermost electron shell is fully filled, it will not lose, gain, or share. Valence electrons with other elements. So this is what I call detail in your answer. If you were to write an answer as detailed as this, you are unlikely to be marked down for whatever reasons. All right. So learn to look at the mark distribution and learn to provide the details needed. All right. Now, next 2D is a very standard question. I'm sure you know by now. Whenever we ask you about isotopes and atomic structure, you must count the protons and neutrons. So both isotopes have the same number of protons, which is 86, and electrons, also 86. However, 220 radon has 134 neutrons, while 222 radon has 136 neutrons. So it's a different number of neutrons. Now, some of you just counted without saying this. Try to also say that 86 means the same number of protons. Okay, you need to still come to a conclusion. You can't just quote data and don't come to a conclusion. All right, so make sure you also have the conclusion in blue. Now, for 2E, I'm not going to go through. For 2E, I'm sorry. The compound's empirical formula is XeF2O3. All right, it's a rather odd compound, but it actually exists. All right. Now, that's the end of question 2. Now, question 2 was directly from the O-levels as well. So this gives you a flavor of the typical types of O-level questions. And if you found them easy, good news, right? I mean, if you found them easy, it means you can handle the content. However, can I just caution you as well? If you found it easy, this means that the cohort might also have found it easy. And that's why we need to really ensure that we provide quality answers. Quality answers means it has details. You elaborate. All right. Now, at this juncture, I finished the first 2 questions. Can I just check that everyone in the Zoom room is okay? Now, if you really want to improve, even if you got the answers correct, you should try to write the answers that I have written down as well. Okay. Now, moving on. A3 was also from the TYS. This one was from 2018 TYS. I think many of you just ignored the instructions. You have to give the names and numbers of each particle in the nucleus. Lithium nucleus contains 3 protons and 4 neutrons. The electrons are not in the nucleus, therefore you don't include them here. So where do the electrons come in? They wanted you to show the arrangement of the electrons. There were a couple of you who left the shells blank. You didn't show the electrons arrangements. Okay, so please read the instructions carefully. This was an actual O-level question, so you need to learn how to not miss instructions out. All right, I believe it's quite easy once you understand the task. Okay, I'm sure you can do this. Now, part B is where, again, we saw the difference between students who gave details and students who didn't. It's very easy to say that lithium and sodium are both from group 1, hence they are similar. But that's not the point, right? By saying that they are both from group 1, you are not adding value to the answer because they already told you that lithium and sodium are the 2 elements. Anyone can tell you they are from group 1. So what must you say? They have the same number of valence electrons. Since they're in group 1, it's 1. But again, this is just a very partial answer. We need to give a 2-mark answer. By saying they all have the same number of valence electrons, it's not really 2 marks. So what more do you say? You can say that if they have 1 valence electron, they all lose 1 valence electron when reacting to form compounds. Or you can say they lose 1 valence electron to achieve a fully filled outermost electron shell, which is the usual thing that we say, right? Now, some of you, your group number, you chose to write 1 and not I. Can you please write the correct group numbers? For your syllabus, you are still using the periodic table where the group number is in Roman numerals. If you don't write Roman numerals, it's actually wrong for your syllabus. All right. Now that's part B. So again, you can see detail is important. Part C as well, detail is important. Many of you knew that sodium is the stronger reducing agent. This one was well known by many students. However, many of you just went on to say, this is because sodium is more reactive than lithium. But you're not answering the question. The question is about reducing agent. You learned this word reducing agent under which chapter? If you think back, reducing agent was taught under the chapter of redox. Hence, your answer must have redox inside it. By saying that sodium is more reactive, it's not really answering the question. All right. So how do you explain this in terms of redox? So you think back. Reducing agents are themselves oxidized. What's the meaning of oxidation? One of the definitions is oxidation is the loss of electron. So you think about oxidation. Oxidation is lose electron. So now you link back to sodium. Why will sodium perhaps lose electrons more readily? It loses electrons more readily because it has more shells of electrons and the valence electron is further away from the nucleus and less strongly attracted. Hence, the valence electrons is more readily lost. So, sodium is more readily oxidized. So, it is a stronger reducing agent. All right. Ken? So your answers, right? I mean, do you always have to have this level of depth? It really depends. If it's 2 marks, 3 marks, yes, I will be expecting this level of detail, okay? So looking at the marks can actually give you a hint as to how much to write. Now, part D, I think most of you could do part D. So part D adds in electrolysis into the question, right? So before we go to part D, can we just check that your part B and C, you have already copied down the level of detail which you will need, all right? Okay, moving on to part D, I think most of you knew that electrolyzing aqueous sodium chloride results in the discharge of H+ ions. Can I please encourage all of us to write state symbols? For situations that you have studied before, this is one of the situations you have studied before, you need to have state symbols. All right? So what do we write? Many of you wrote things like hydrogen is preferentially discharged. No, it's H+ ions. H+ ions are preferentially discharged at the cathode. It's the ions that are preferentially discharged, not the gas, not hydrogen per se. And of course, this forms H2 gas. And why are H+ preferentially discharged? Because sodium is above hydrogen in the reactivity series. All right. So this is how you can phrase your answer. You have to make sure that your half equation is correct. Now, many of you went on to write a half equation for the anode. That is not necessary because over here, we are looking at sodium metal. Sodium metal, if it forms, it should only form at the cathode. So we should only look at the cathode half equation, not the anode one. Okay? All right, and that concludes the third question. The third question was basically more or less the TYS question with a few parts added in by me. All right, moving on to the fourth question. Now, the fourth question really tests whether you can make full use of the context and information given to you. Now, the main topic in the fourth question is, of course, separation techniques, which has not come out in paper 2 for a long period of time. So separation techniques has not appeared in paper 2 for at least a few years already. So to do well in this question, highlight chemical names. Highlight numbers. That will really help you. Now, after you highlight chemical names and numbers, it's time to highlight the descriptions, but don't highlight every single thing, please. You highlight and focus on words like powder. Obviously, powder, you have learned it under speed of reaction. It has an impact on the speed. You highlight chemical names. Dichloromethane and water, which dissolves the coffee and the caffeine and the tannins. And then step 2, we would separate what? So in step 2 is separation, but separating what? Coffee powder. Powder from the liquid mixture. Now, this is really crucial. If you had paid attention to step 2, you would have gotten the answer correct because you are separating a powder, which is a solid, from a liquid mixture. And only in step 3 do you use separating funnel. So this is a series of separations. Next, you are given some information. Caffeine is completely soluble in dichloromethane, but only slightly soluble in water. This is important. It means that it's not insoluble, it is slightly soluble. Some caffeine will dissolve in water. This has an impact later on when you use separating funnel. Some of the caffeine will be with the water. Next, tannins are insoluble in dichloromethane but soluble in water. So tannins go with water. Next, the densities are crucial. For separating funnel, you must know the densities because you must predict dichloromethane will sink. It's the bottom layer because it has a higher density. Finally, the boiling points of caffeine and dichloromethane will also help to guide your answers. So once you have highlighted the relevant chemical names and numbers, you would have figured out roughly what's going on. So I asked you to name the separation technique to separate powder from liquid. Powder is a solid. Solid, you separate it by filtration from a liquid. Next, using ideas about collisions to suggest why the coffee powder must be ground to a fine powder. By grinding to a fine powder, the surface area to volume ratio of the particles exposed for reaction increases. Now, surface area to volume ratio is a very important phrase here. So fine powders have smaller particle sizes. That's why their surface area to volume ratio exposed increases. This increases the frequency of collisions and frequency of effective collisions between reacting particles. making the reaction faster or the dissolving faster. Now, most of you knew the broad explanation, but many of you missed things out here and there, and as a result, you won't get the full marks. All right, so let's learn, okay? Whenever we are grinding to a fine powder, is the surface area to volume ratio that increases. All right, Ken? Sorry? Yes. Okay, now, so that's part B. Now let's move on to part C, D, and E, which are more exciting in my opinion. Now this is a separating funnel, top layer, bottom layer. Now please don't assume water is higher density and will sink. In fact, over here is the reverse, right? The water has a lower density and will float. So water is the top layer. Now with the water, what is dissolved? If you read the information on the previous page, it is the tannins which are dissolved. The tannins are completely soluble in water. With the dichloromethane, what's dissolved? Caffeine. Caffeine is very soluble in dichloromethane, and therefore caffeine is found with the dichloromethane layer. Now, obviously, this is the correct answer already. However, if you think about it, just now we mentioned some caffeine will dissolve in water as well. All right. So this is the answer for part C. How do you locate the caffeine, tannins, dichloromethane, and water? All right. Next, for the very final step, step 3, the caffeine will need to be extracted from solution. Suggest a suitable extraction technique. Now, there are two answers for this. You either use fractional distillation, as caffeine and dichloromethane are miscible and have different boiling points. This is one answer. However, it is actually more common to use crystallization to extract caffeine. All right. Why is crystallization suitable? Because caffeine dissolves better in hot dichloromethane than cold dichloromethane. Now, you didn't know this, that's why you didn't have written it. But if you actually read up, okay, on Google, this is how you extract caffeine. You actually crystallize it out, but fractional distillation also works. All right, so that's for part D. How would you separate caffeine from its solution? Okay. And now for part E, the mass of caffeine extracted is actually less than the actual mass of caffeine present in the coffee beans. Now, if you had paid attention to the data just now, you would realize why. Why is it that the yield of the caffeine extracted using the dichloromethane layer is less than the actual mass of caffeine? If you look at the separating funnel we said just now, not all the caffeine is in dichloromethane. Some of the caffeine is with the water. The caffeine is slightly soluble in water. So some caffeine might have dissolved in the water. And remember, we didn't take the layer of water subsequently. So this resulted in some loss of caffeine. Okay? And that's for part E. Okay, we are doing good on time. Now, we have a next part F, right? So this is about MSG. So monosodium glutamate is a sodium salt. It's a common flavor enhancer. It enhances the flavor of food. It's made by titrating glutamic acid with an alkali. The alkali must contain sodium. It is not sodium metal. It's not sodium oxide. The alkali must be the hydroxide. We know that because alkalis must dissociate and ionize to give hydroxide ions when dissolved in water. So the alkali must be the hydroxide. Next, part F. This is just the crystallization steps. So you should know the crystallization steps very well by now. So please refer to your salt prep notes to do part F part 2. All right? This is the crystallization steps, the very last 3 steps when obtaining a salt. Now, A5. Now, A5 is about the carbon cycle. As we have said, there are certain topics which have not really come out for the past few years. The carbon cycle is another example of this. The last time the carbon cycle was tested in paper 2 was more or less in 2017. All right? So you need to be able to describe the carbon cycle well. Now, many of you, I gave you 3 out of 3 for this part. However, your answer is actually not 3 out of 3. Many of you had neglected to even name the reaction. Many of you just wrote the equation, which is rather odd because why would you write the equation without saying whether it's photosynthesis or respiration? You need to state the reaction's name before writing the equation. Now, these equations are not easy to balance and write. I'm glad to see that most of you remembered how to balance, but I hope this is content that we already have in our heads. You must not be able to forget this content. Now, once you have written the chemical equations, half the battle is won. The next part, though, was very poorly expressed. Many of you said photosynthesis takes in carbon dioxide. But many of you are missing out words. We are asking how does it regulate the amount of carbon dioxide in the atmosphere? So it's important to tell me, is taking in CO2 from the atmosphere? This is an important phrase. While respiration gives out or increases the amount of CO2 to the atmosphere. All right. So this is an important phrase, are the words in red. Now let's move on to the words in green. If the rate at which CO2 is removed from atmosphere by photosynthesis is balanced with the rate at which CO2 is given out to the atmosphere by respiration, the amount of CO2 in the atmosphere remains regulated or constant. Now, the words in green were actually missing in many of your answers, but I still tried to give you as many marks as I could. But can we please write down this answer? Even if you had gotten full marks 3 out of 3, can I advise you to write this down? Let's take about 2 minutes to write this down. All right, B part 1. I think most of you knew the raw materials: hydrogen, nitrogen. Now, the source of the raw material: cracking of large hydrocarbons in crude oil or just cracking of crude oil. Nitrogen, fractional distillation of liquid air. Now, a lot of you did not write liquid air. As I mentioned today in class, it's good to write it. Now, part 2 was the problem. Now, many of you were lost in part 2. Suggest one reason why the use of chemical fertilizers derived from ammonia would increase the amount of CO2 released to the atmosphere. Many of you said things like, oh, because the hydrogen is obtained from cracking, cracking produces CO2. Now, that is incorrect. Cracking itself does not produce CO2. All right? So how do you express your answer? You know it has something to do with hydrogen and crude oil. Hydrogen is obtained by cracking of crude oil. Which is a non-renewable fossil fuel. All right? So where does CO2 come in here? Now, the CO2 doesn't come in cracking. The idea is because it's a fossil fuel. Because it's a fossil fuel, it produces CO2 and releases it to the atmosphere when combusted. That's the idea. The idea is the CO2 is produced through combustion. Okay? Cracking itself doesn't directly form CO2. The idea is that you are using crude oil. So by using crude oil, you are encouraging the use of non-renewable fossil fuels, which obviously releases CO2 when burnt, when combusted. Okay? So that's it for question number 5. And then we move to question number 6. All right? Okay, so moving forward to question A6 right now. If you read A6, some of you might have found it familiar. This is because question A6 was obtained from the 2017 TYS. Just that I modified things here and there, but it's essentially the same concept being tested. So A6 is obviously about rate of reaction. So when we say rate of reaction, your mind should immediately go to, oh, what factors will affect the rate? Concentration is one. Temperature is another one, right? So if you just look at this entire question, it's about rate of reaction, concentration, and temperature. So the first thing is to write the equation correctly. Now, some of you, the equation, I think most of you could write, but it's the state symbols that pose problems. Some of you had thought that CuCl2 will be a solid, but it's not. Copper 2 chloride is soluble in water. All chlorides are soluble in water except LS, lead 2 chloride, silver chloride. Okay? Next, B part 1. One of the experiments was conducted at a higher temperature. Which one? Most of you knew it was experiment 2. But how do you explain that? All right? Now, it is important to state that experiment 2 has the same concentration and volume of HCl as experiment 1. So this is the idea of keeping variables constant. You had used the same concentration and volume of acid. All right, keeping variables constant. Then you see the experiment 2, the time taken to collect 10 cm³ of gas was shorter at 15 seconds compared to 30 seconds for experiment 1. All right. This indicates faster rate for experiment 2, which could point to higher temperature. Now you must compare 2 with 1 and on top 2 with 3, because in number 3, you change the concentration. Okay, so I think many of you, even though you got full marks, you had not written this, the phrase highlighted in yellow. So it's important to show awareness that you are keeping variables constant. All right. Now, B part 2, again, many of you lost marks. Why did you lose marks for something that was in the notes? I think it's because you had selected which phrases you want to include. You wanted to write less. But when you write less, you don't necessarily get the full picture in your answer. Remember, what is being marked and assessed is what you hand in. So if you write less, would you regret it later on because you had given less details? So higher temperature means what? Higher temperature means that the particles gain kinetic energy and move faster. Now, many of you wrote this because this is intuitive, it's shorter. But many of you did not write the next phrase, which costed you 1 mark. So what if they gain kinetic energy? The number of reacting particles with energy greater than or equals to the activation energy increases. So many of you had left this out. That's why you got a carrot from me, right? You missed something out in between, which is this, the sentence in red. The idea is as they gain energy, then you have more reacting particles which possess energy greater than or equals to the activation energy. This increases the frequency of collisions and frequency of effective collisions between reacting particles. Okay, so most of you had the sentences in black. I think it's just a sentence in red that a lot of you missed it out. Okay, so just ensure that you have taken down the answer for B part 1 and B part 2. Okay. Okay, now we are at part C. Now, part C is about proving something. Now, obviously, you have to use some mathematics to prove, right? Okay, I think most of you knew the mathematics to prove it. However, the way you presented it was very, very awkward. Okay, so guys, how do you present something like that? I'm sure you know, all of you knew you have to calculate moles. To calculate moles, you use NCV, right? So C times V, literally. All of you can do this. All right, so all of you could do this. However, can I just say that the next part, the presentation was really, really not great. All right, can we just focus on mole ratio? You must have shown me the mole ratio. So it's 1:3. Now, many of you got here and stopped here, which is not wrong. It's okay, I think. However, there's a way to improve, right? Can you at least make sense of the 1:3 in a sentence? The 1:3 means 1 mole of citric acid requires 3 moles of KOH for neutralization. This means 1 mole of citric acid produces 3 H plus ions. Okay, great. So we should have written this sentence out. All right. Let's do it. All right. Now, most of you, I believe you didn't have the sentence lah. Now, if you don't have this sentence, would it cost you the mark? I don't think so, personally. However, can I just say that if you don't have this sentence, I feel that you're always lacking something in the answer. A student who can do well will be a student who can do both the calculation and the meaning behind the calculation. Okay, so that's it for C part 1. Now for C part 2 is a titration curve, which I'm sure most of you could interpret. But again, the wording I felt was very awkward at points. Okay, so C part 2, you are given a titration curve. Now, many of you didn't know how to describe this. There are many ways to describe this. You can call it the endpoint. You can also call it the region of sudden pH change. Clearly, endpoint is shorter, probably easier to remember. So we are going to use the word endpoint. Basically, that region is the region of interest. The endpoint is actually midpoint of that segment. So if we just look at the midpoint, it's about pH 9, about pH 9. So what do you write? Why is methyl orange not suitable? The pH at the endpoint of the titration changes from pH, say, I think about 6 to about 10, which is outside of the pH range where methyl orange changes color. All right, and that's all you need to write. So at Pure Chem, you will need to be able to suggest which indicator to use. Methyl orange is just not suitable because it changes color too early at pH 4 to 6. Okay? Now, once we have done this, I think this one is quite straightforward. The next one was not well done. Part 3 was actually very, very poorly done. So I would like all of us, regardless how many marks you got, to really take down the answer. Now, there are actually 2 parts to this part 3. Firstly, is the time taken is longer. This is the first thing you must explain. The second thing you must explain is the volume is 3 times higher. These are 2 separate points altogether. You must have 2 separate parts to your explanation. So why? The time taken is longer because citric acid is a weak. And because it's a weak acid, it dissociates and ionizes to produce a low or lower H+ ion concentration when dissolved in water. All right. Ken? Now this is something that I think you should write. It's good to go on to say the frequency of effective collisions between reacting particles decreases. So the reaction is slower. Now, this is just part number 1. All right. Now, like I said, many of you probably didn't think of talking about collisions at all, but I would say it's relevant. Now, number 2 is to explain the volume of gas. Now, when we learn speed of reaction, I believe when I went through the graphs, we were very disciplined. We said, right, the graph has 2 parts. The first part is the speed, the gradient. The second part is the volume of gas, which depends on number of moles. Citric acid. Citric acid, all right, produces 3 times the number of moles of H plus ions compared to hydrochloric acid. So the idea is moles. Some of you said, oh, citric acid has 3 times the concentration of H plus. Actually, that's incorrect because you already know that citric acid is a weak acid. So the concentration need not be 3 times. But eventually, when all the citric acid reacts, it should produce 3 times the number of moles of H plus. All right? So it produces 3 times the volume of CO2. Okay? So the idea is moles. The idea of moles must come out in order to explain volume of gas, the final volume of gas. Okay? Now, as mentioned, the database question was a very real life scenario. It's the chemistry of ice cream. Okay, I'm sure you know by now what to pay attention to in a database. The title, the definitions, as well as the trends and patterns in data. Trends and patterns are particularly important here. You realize they got 2 types of ice cream, standard and soft serve. Now, soft serve ice cream is a bit like McDonald's ice cream. All right, McDonald's ice cream is like soft serve. It's usually quite soft, okay, melts rather quickly. All right, now, what's the difference? So let's look. Water, not much difference. Fats is different. Soft serve, lower fats. Standard, higher fats. Sugar, not much difference. Emulsifiers, flavorings, not much difference. So you look, oh, so only the fat content is significantly different. And that has impacted the freezing points. Now, the freezing point is lower for soft serve. Now, can we please take note, negative numbers, some of you are not very good with it. Okay, -6 is a lower freezing point. Some of you thought -6 is a higher freezing point. That's incorrect. -6 is a lower or smaller number. Okay? Now, freezing point is also called melting point. It's the same thing. Right? You melt and you freeze at the same temperature. So if the freezing point is lower, what it means is that it melts more quickly. So McDonald's soft serve ice cream generally should melt more quickly than, say, a standard tub of ice cream. Next, importantly also is how we freeze the ice cream, right? So I've told you that, oh, you need to pump a liquid refrigerant. This is the key. It's a liquid that's used to freeze the ice cream. How does it freeze the ice cream? It cools it down. However, this is where it's important. If the crystals are too large, the texture will be grainy. This is a pattern, a trend. Then you go on, the size of the crystals depends on speed of freezing, trend. The more quickly the ice cream mixture can be cooled down, the smaller the crystals, trend. So you should have highlighted these 3 start sentences. So the idea is, I want small crystals. To have small crystals, you must cool down quickly. Then it will be nice to eat. So if you look next page, I have 3 different refrigerants. Which one will cool down most quickly? Obviously the coldest one, right? The lowest boiling point means that it will be the coldest liquid. For nitrogen to become liquid, we must cool it down to minus 196 degrees Celsius. This means that liquid nitrogen is at minus 196. It's so cold. If it's so cold, it will be able to cool down your ice cream most quickly. All right. And next, we move on to something else, emulsifiers. So ice creams contain a large proportion of fats. And this is a typical fat. You can see that the fat contains the ester linkage, something that we have been doing for the past time practices. Fats contain ester linkages. Now, fat molecules are usually immiscible with water. Therefore, you must add emulsifiers and stabilizers to ensure the fat and the water mix together. They also help to ensure the ice cream doesn't melt. Finally, freezing point depression. So obviously, when you have impurities, it will depress the freezing point. Any equation must be paid attention to. All right. So basically, impurities like salt and sugar will decrease the freezing point. And that's why salted caramel ice cream, salted caramel has salt and sugar inside it, it will have a lower freezing point. Okay? And now let's answer the questions. Describe and explain one piece of information from the table which proves that ice cream is a mixture. Well, number one, there are two actually. Number one, there is no fixed composition of the substances in ice cream. For instance, the fat content for standard ice cream is 7 to 10%. So that means there's no fixed composition. The second piece of evidence, probably that you spotted, is ice cream freezes or melts over a range of temperatures. All right. So take for example, -6 to -1 for say soft serve. Okay. Now next, the next part 2 is really just KPT. So standard ice cream is served at -10. What if I warm it to 10 degrees Celsius? So clearly it's going to melt, right? It's going to change from solid to liquid. The way to answer this, the arrangement of particles changes from closely packed in a regular manner to closely packed in an irregular manner. All right, so that's arrangement. Movement. The movement of particles changes from vibrating about fixed positions to sliding over one another easily. Now, this question, I felt that a lot of you, it's either you knew it or you didn't, right? KPT. Okay, that's part 2. So remember, for KPT questions phrased like this, you need to say the arrangement changes from something something to something something. All right. The movement of particles changes from something something to something something. All right. This is how it's phrased to get the marks. Now, part 3, I think most of you knew this. If you lost marks for part 3, it's the phrasing. A student suggested the freezing point of the ice cream depends on fat content. It's what I said just now. Okay, so explain why the information supports this. First, you should give the relationship. The higher the fat content, the higher the freezing point. Many of you jump straight into quoting the data without giving the relationship. Remember, you are quoting data to prove a conclusion. You must state the conclusion, which is this. All right, so this is very important. Once you have done the conclusion, relationship, then you go back and see the data. Oh, what must I quote? Oh, I must quote that. Oh, if the fat content is like that, then the freezing point is higher at like that. So for example, standard ice cream contains or has 7 to 15% fat. So its freezing point is higher at minus, I think 2.7 degrees Celsius, is it? To 0.5, is it? I can't remember. Soft serve has 3 to 6% fat. So its freezing point is lower at -6 to -1. Right? So remember to give the conclusion. I feel that a lot of you just didn't bother giving the conclusion. Now, next one, Freon 13, I think most of you can draw. I'll just quickly draw it on my side. It's quite straightforward because you only need to show outer electrons, so not much worrying. All right. Now, when you decide to use different symbols other than dots and crosses, can you please ensure you have a legend or a key? All right. Okay, so for example, carbon is like that. Fluorine is like that. Finally, last one, chlorine is like that. Just add a simple key, all right? So this is Freon 13, CF3Cl. Now, of course, the next question is, so how is Freon 13 damaging to the environment? Okay, it's quite clear. It contains CFCl, right? So Freon 13 is a chlorofluorocarbon, which I think most of you wrote damages the ozone layer, reacts with ozone, but I think a better word is depletes the ozone layer. All right, so if it depletes the ozone layer, what's the issue? It allows harmful ultraviolet rays to reach the surface of the Earth. The ozone layer prevents ultraviolet radiation that's harmful from reaching the surface. Okay, next, state which refrigerant in table 7.2 will be most suitable for creating ice cream with the least grainy texture. Least grainy, smallest ice crystal, so it's nitrogen. Why nitrogen? As it has the lowest boiling point of minus 196 degrees Celsius, so it can cool down the ice cream most quickly to form smallest ice crystals. So using liquid nitrogen to create ice cream generally creates ice cream that is smoother, less grainy. Now, next, the fatty acid molecule. I think if you got it wrong, it's just a matter of you did not pay attention to the atoms. You don't have to draw all the CH2 out. You really don't have to. You could leave it like this. Unless they ask for full structural formula, this drawing alone would be sufficient. So that's part C for question number 7. Now, for part D, I'm not going to go through. For part D, I think it's just a matter of using the formula for freezing point depression. Okay, so I hope you refer to the formula. Remember, the formula requires you to convert to moles. You must convert 20 grams of salt and 20 grams of sugar to moles. You do so by dividing by the MRs. MR of sodium chloride, MR of sucrose. So please try part D yourself to ensure that you are able to do it. Now let's move on to the most chaotic question of this paper, which is the question 8. Now, question 8 was more or less taken from the TYS as well. It's taken from, I think, 2018 TYS, something like that. It was 2018? No, 2016 TYS, all right? Now, you have to take every single column one by one. So let's do density first. Now, density is in grams per dm cube. The units already help you, right? What does grams per dm cube literally mean? It means how many grams in 1 dm cube. So how would you then go from the data you're given to density? You are given volume of 1 mole in 1 dm cube. Volume of 1 mole. So what does this literally mean? This 17.2 means what? 1 mole of ethanol is 17.2 dm cube. 1 mole is how many grams? You will calculate. If you calculate 1 mole is how many grams? We use M and MR. Find mass, number of moles times MR, 46. 46 grams is 17.2 dm cube. Right? 1 mole is 46 grams. So what do we mean next? What do we do next? I need to go to 1 dm cube. How do I go to 1 dm cube? To go to 1 dm cube, I must divide by 17.2. That means this side, I must also divide by 17.2. So 46 divided by 17.2 is what? So now you have to do your calculations, right? Okay, so 2.67. Wait, give me a minute. Give me a minute. Sorry for those in the Zoom meeting, we'll ignore this question first, okay? I think I made a mistake with one of the numbers. I think 17.2 was the wrong number that I made. Okay, but never mind. We just move on first to the rest. All right. Now, so you realize that, okay, we have density. Now, density is mass over volume, right? So now you want to find volume of 1 mole at room temperature and pressure. So volume is equals to mass over density. Okay, now you don't have mass here though. What you have is you have 1 mole. So 1 mole is what mass? So you must take the MR. MR is the mass of 1 mole over density. All right. So what do we do to get this volume of 1 mole? You take the MR of octane, divide by the density. So 114 divided by 703, that gives you 0.162. That's correct. Okay. Next one, volume of 1 mole of fuel. Hydrogen is a gas. 1 mole of hydrogen occupies 24 dm³. All right. Next, let's do the enthalpy change when 1 kilogram of fuel is burnt. Now, this is particularly important. You need to realize that 1 kilogram is 1,000 grams. So you will need to now convert 1 kilogram to 1,000 grams, and then 1,000 grams you need to convert to moles. All right. So if you do it correctly, you should be able to obtain these answers. Okay. Now, this was not a well done question because I think many of you didn't know what the calculations to be made were. Okay, it's very important to realize that 1 kilogram of fuel means 1,000 grams. Then you must convert to how many moles? How do you convert grams to moles? You have to divide by the MR. And I think many of you did not realize that. Now, once you have moles, you have to times multiply to the enthalpy change for 1 mole. Okay? Now, I will just demonstrate using octane as an example below. All right, so I'm just going to go to octane. Now, 1 mole of octane releases 5075, I think, kilojoules of energy. So you got to ask yourself, 1,000 grams of octane is how much? 1,000 grams of octane, you take 1,000, divide by the MR, which is 8 times 12, 18 times 1 moles. All right. So you convert to moles first. That's 8.77 moles. So now 8.77 moles, how much energy will it release? So 1,000 grams of octane is 8.77 moles. It will release 8.77 times 5075. 44,517 kilojoules, which is 44,500 kilojoules. Now, it is important to put back the sign because they're asking for enthalpy change. It's all exothermic, so it needs to be negative. Okay? Ken, many apologies for the error for 17.2. I think 17.2, the ethanol volume is not correct. So let me take it back. Okay, I'll change the value and I'll let you all know next lesson. Okay? But the rest of the answer should be correct. 0.162, 24, minus 44,500, minus 143,000, and minus 29,700. All right. Now moving on to the next question, which is a hydrogen fuel cell. Now, can I just point your attention back to some obscure parts of the syllabus which you may have missed out? Okay, one of the obscure parts of the syllabus, of course, is the hydrogen fuel cell. All right, you have learned electric cells under electrolysis. You know that electric cells, they convert chemical energy to electrical energy. Similarly, the hydrogen fuel cell does the same. The hydrogen fuel cell converts chemical energy to electrical energy. So can I just point your attention back to our notes? Now, hydrogen fuel cell is found right at the end of energy changes, which is why you might have missed that out as you were revising, because you didn't realize that it was part of energy changes. All right. So these are the half equations which you will need. Some of the half equations perhaps look a bit strange to you, especially the one involving the anode oxidation of hydrogen. All right. So can I point your attention back and revise energy changes so that you know the half equations for the fuel cell? It's under energy changes, it's not under electrolysis, that chapter. So now let's just finish with the fuel cell for today. So what are the half equations? So first, we have the anode. At the anode, this happens. Now, this is an alkaline medium. All right, I hope you realize this is an alkaline medium. Okay, the cathode. Sorry. For the cathode, perhaps what's a little bit surprising to you, this is actually the reverse reaction of the electrolysis of water. All right, so after writing these two half equations, you realize that, oh, actually what we are doing is we are getting hydrogen and oxygen to react as separate electrodes. The two electrodes are separated and there are electrons lost, electrons gained. The electrons can move in the wire, in the circuit to power the circuit. So why is this more environmentally friendly? This is because the hydrogen fuel cell only produce water, which is not a pollutant. Now, don't stop here. They are asking, why is it more friendly than burning octane? So you should say, burning octane releases CO2, which is a greenhouse gas. Okay? So please go and study the half equations for the fuel cell, which is under the chapter of energy changes. Now for part C, I don't really want to go through. This is under chapter 23, enrichment. Under chapter 23, enrichment, I have done up a comparison table of the differences between ethanol obtained by fermentation and ethanol obtained by hydration of ethene. Can we please go and learn why is it that ethanol obtained by fermentation from glucose is much more environmentally friendly? It's under chapter 23, enrichment. All right, so if I point your attention back again to notes, there are many notes that you may have missed out along the way for some reasons, but this is chapter 23, enrichment. You can clearly see it's written there, highlighted in yellow, the environmental impact of using this ethanol as fuel. All right, so with that, we have more or less finished the review of time practice 4, except for the either or questions. All right, I will fill up the remainder of the answers and I'll let you know when it's done so that you can do the remainder of your corrections. Now for the either or, you can see it was all about bonding. So if your concepts in bonding are no good, please go back and study chapter 7, covalent bonding, particularly the giant covalent lattices. Okay, so with that, it's 6 o'clock. I will end the review of time practice 4 here. For tomorrow's lesson, it's a combined class. I need all of us to bring the practical that we did the last time round, as well as the prelim paper along. All right, so thank you. For those in the Zoom meeting, I shall stop the recording here.